Good morning, ladies and gentlemen, and maybe for some of you, good afternoon. I hope I'm audible. In case you have issues or can't hear me, please use the chat so I can see if there are issues. If you have questions, please use the Q&A option. So I have the menus open so I can follow here if there are notifications from your side. So once more, good morning or maybe good afternoon. My name is Ben Maathuis. I am working at the Department of Water Resources at ITC. And this morning I would like to discuss and introduce you further to the cloud services available using openEO and let's say also introduce you a bit to the additional capabilities we have developed using the Python version of ILWISPy. Currently, a lot of developments have been ongoing, which have resulted in the fact that we are now dealing with basically a continued exponential growth of big EO data, and next to that also a lot of technological advancements over the last, let's say, 10 years. These result in fundamental changes how EO data is being stored and how users access, process, and use the data. In the past, we used to bring the data to the software, but basically now it's the other way around. We are bringing the software to the data, and that is basically what I would like to show a bit during this session. Instead of downloading EO data and processing it on your local machine, you as user can now specify a virtual machine in the cloud, and with this virtual machine you can access, process the data and transfer maybe intermediate results or end results to your local machine in order to then use that and provide it to the end user. To facilitate this, a number of years ago, the openEO API was developed, which is offering possibilities to have a standardized communication and hiding architectural differences between various cloud platforms. So openEO can be used to connect to big Earth observation cloud backends like Copernicus, Google Earth Engine, Vito. So using your Python or R scripts, the request to get and communicate with the various backend providers is basically standardized and using predefined functions in order to access the data, retrieve the data, or process the data at these various backends. So basically, with an internet connection, and this morning we will use our, let's say, local resources like my laptop, using a web browser access to the Innovation Lab, where we specify our virtual environment using a Jupyter notebook with Python and a number of scripts in order to access and process data from the various cloud services. I have listed a number over here, like Copernicus services, openEO, the data store at EUMETSAT, which can all be accessed using an API. But we also have the openEO cloud services, like, again, those from Copernicus, Google Earth Engine, or the Flemish Institute of Technology, where we have this homogenized access to these various services. Apart from that, we have a lot of other cloud services providing big EO data and analysis-ready data, like those from the FAO or, let's say, the soil database at ISRIC. So you have the possibility now of using all of these various big data repositories, transferring what you want to your virtual environment in the innovation lab, and then subsequently download only the end result to your local system, and eventually combine that with other local data in order to provide that information to the end user. It has got some repercussions. You have to get a bit more familiar with the scripting languages. So in this case, mostly Python is being used, but I can imagine that some of you also are more familiar with R. But anyhow, we divert a bit from a graphical user interface to coding and scripting. And please take into consideration that it requires time to learn any of these scripting languages. Another essential element is that you have to get familiar with the various cloud data resources and their access, and also making use of the application programming interface. When using Python, you will also use different side packages. So all of these have their specifics in terms of pieces of code, how they are used. And one of these side packages I'm going to demonstrate this morning is ILWISPy. And last but not least, as these virtual environments are mainly created under a Linux environment, you also have to get a bit more familiar with Linux so that you are able to find your way also using some of the common terminal commands. For those of you who are teaching, it also implies that you are likely going into a new teaching approach, which is making use of Jupyter notebooks, where you have the possibility of using code, so your coding, together with markdown fields which provide explanations of the code which has been provided. At ITC, we try to support this by developing software tools. ILWISPy is one of these examples. We have developed it in such a way that you can run it under a Windows environment on your local PC, but you could also install it in a cloud-based repository under a virtual environment, and then together with other libraries, you are able to process the data, download your results, and then we are using ILWIS 386, or you can use QGIS in order to visualize the data at your local laptop or local computing system. We are encouraging our staff and students to work more and more with Jupyter notebooks. And once they have prepared their notebooks, we are reviewing and going through a process of quality control, and then we are, let's say, trying to put these in the near future in a GitHub environment so that all of you are able to use this information containing software, Jupyter Notebook scripts, as well as sample data, so you can reuse these resources for your own applications. But that is, let's say, work in progress. I have registered and signed in into the EO Africa Research and Development portal. So I assume that most of you are familiar with the portal and have been using it. If that is not the case, then review the information provided at this link, register yourself, and try to get access. I have prepared a notebook, which basically is showing you the first steps using openEO and ILWISPy in the Innovation Lab. I'm going to import the required libraries. So here you see I'm importing ILWIS. I'm importing openEO, the operating system, NumPy, and matplotlib. So this is what we are going to use within this notebook. In order to get an idea of the ILWIS version we are using, you have an expression, an ILWISPy expression over here showing you the version. And we have, let's say, in order to get an idea of what is available currently under ILWISPy, we can create an alphabetical listing of all the operations that are currently available. And ILWISPy is returning us with the operations at our disposal. So hydrological flow operations and all kinds of GIS, remote sensing, and generic raster operations, supporting also vector-based operations. And one of the important ones is, let's say, our map calculator, which allows us to do all our raster calculations. But there are options like filtering, creating of relative dams, doing the resampling of remote sensing images to a different coordinate system and projection, etc., etc., etc. Temporal filtering is another one, creating zonal statistics, etc. So these operations are at our disposal. Now we are going to create a folder because we are going to download at a later moment some satellite images from cloud repositories. If the folder is already there, it will be retained. Now I'm going to assign the folder as our working directory for ILWISPy. So basically, this is the preparatory work. We have loaded our site packages and we have defined where the data will be residing. So now we are going to have a look at the openEO. openEO is having a number of providers, so back-end providers like the Copernicus data space ecosystem, which is providing global data. Google Earth Engine, for example. We have a number of data providers which basically provide European data. We have the Sentinel Hub. We have the one from the Flemish Institute of Technological Development. You want to know a bit more about openEO and the philosophy behind, then review this article published at ResearchGate. Additional information on openEO and on the client is provided using this link, so that can be reviewed as well. So let's continue with our code. Let's first have a look at the version we are using, 0.25. In case there are any other tokens for access, I'm going to remove them. And now I'm going to establish a new connection with the openEO data space at Copernicus. So I'm going to authenticate myself. And I have logged in. And I have been authorized successfully. I can get a list of processes openEO is supporting. So in a similar way as I have shown you the listing of ILWISPy with the functionality and the operations that are at your disposal, openEO also has a number of operations that can be used in order to conduct the processing. So in this case, under the openEO at Copernicus, 132 processes are being supported, offering you all kinds of processing capability as they are provided over here. And for example, clipping. If you activate the item, you get an example on how to use these type of operations and how they can be used in a processing string. So a lot of operations at your disposal, and an important one which we will use later is also the median function. Another important element is to get an idea of the lists of collections that are available at our selected openEO backend. So the openEO at Copernicus is providing you direct access to the full repository of Sentinel-3, Sentinel-5, Sentinel-2 Level 1C, Level 2A, as well as the Sentinel-1. And next to that, other missions, and that will be expanded in the future, like the Copernicus 30 is the global elevation model derived from the SRTM, so the Shuttle Radar Topographic Mission, and being reprocessed, as well as a repository of Landsat 8 level 2 data. So let's now review one of these collections. For example, the atmospherically corrected Sentinel-2 level 2A. So we see over here a description. We have a preview. It says that the data is available as from the mid of 2015 onwards. The various spectral channels, as well as other ancillary data that is being provided. Again, the temporal resolution, the spatial resolution, as well as information about the projection and the georeference. So Sentinel-2 constellation information, platforms 2A, 2B, then the details of the spectral channels that are available, as well as the ancillary information and the units. With the option of the cloud cover, and you have a number of links that provide you with additional information. Now I'm going to connect to another openEO backend, which is the one at the Flemish Institute of Technological Development. So again, I authenticate myself. And I have logged in at Vito. So I'm now at a different backend provider. And I could have also used Google Earth Engine or one of the others as was indicated before. I'm now retrieving over a certain time period Sentinel-2 level 2A data for a specified window with a coordinate system EPSG 4326. So latitude, longitude. I'm assigning my temporal extent defined over here, and I want to extract the 10-meter spatial resolution spectral channels in the visible blue, green, red, and near infrared with a minimum cloud cover. So I'm defining this selection. Within this temporal domain, there are quite a number of Sentinel-2 level 2A recordings. But in the end, I want to have only one spectral channel returned, and I'm using a median function for that purpose. So having defined my data request, I now am going to download my data into the folder which I have specified over here. So now we have to wait a few moments until the data is being retrieved and until this asterisk turns into an executed piece of code, and then it will get a prefix number 15. So we are now from the openEO Vito downloading the data into our virtual environment on the Innovation Lab at EO Africa. If you have any questions so far, don't hesitate to use the Q&A. Or if you have any other things you would like to remark, please put them in the chat. I have already, let's say, been processing the data a bit before. So you see over here, and let me remove some of the other information. The file img1 is already created, but you can see that the size is still 0 bytes. So we still have to wait for the content of the file. I've run the notebook a couple of days ago, so I have created a backup. So if everything works out, we should get a file in the order of 42 MB. And that is what we have now. So you see that the field has been executed, and now we can use ILWISPy in order to do some image processing. So we are loading the retrieved raster image. So you see that the image size in terms of rows and columns and the number of spectral bands is meeting the 4 spectral bands we requested. Now we are selecting the first raster layer is our blue, the second one the green, the third one will be the red, and the fourth will be the near infrared. But the numbering in Python is starting from 0 and not from 1. So we have now 4 variables: blue, green, red, infrared. The size is being printed in terms of X, Y, as well as Z for the IR variable. So the number of X, Y, and Z, of course, one spectral channel. We can subsequently calculate some of the statistics. So an ILWISPy function is to derive the statistics, and here you get the full listing of the statistics for the different pixel values in the infrared channel. We can get the minimum, the maximum, the average, the number of pixels. So that is what you see over here. And of course, using matplotlib, we have the possibility to create a simple plot. So you see over here, the full data range of the image, as it is a 16-bit integer. Given the data range and our display options on our screen, we would like to stretch, and even omitting the 1% tails, we would like to stretch it to 0 to 255 so we can display it. So we are conducting a linear stretch over here using the minimum %1, which is our minimum cutoff value, and then the maximum %1. And then we are resetting the values from 0 to 255 with a precision of 1. And we do this for the 4 spectral channels. So basically we are conducting the linear stretching and setting our value range so that all the data now, instead of having this data range from 0 to whatever, 12, 13,000, will now be in a range from 0 to 255. Once that is done, we can transform the ILWIS stretched raster layers into a NumPy array, which then allows us to display the data in matplotlib using imshow. If you want to visualize the data in ILWIS, then you would have to download. So here we are just using NumPy and ILWISPy and matplotlib in order to visualize the data. So in order to do that, ILWIS has a function which is called iter, which basically reads each and every pixel, pixel by pixel, line by line, and then transforms this into a one-dimensional array, and then subsequently it is reshaped using the NumPy reshape into a two-dimensional array using the dimensions of the rows and the columns of our initial satellite image. So now all the pixels from the 4 spectral channels are being read. If you would multiply 2526 times 2643, you would get an array of this dimension as a one-dimensional array. So basically in a column, a single column. And that single column in NumPy is then reshaped back to a two-dimensional array. And if I use the NumPy shape statement, you see it is nicely reshaped back. But now in a format that it can be visualized using matplotlib. So the last thing we are doing is we are creating data stacks. One data stack, which is showing us the false color, which is composed of the infrared, the red and the green, and another data stack which is composed of the spectral bands red, green and blue, so the natural color composite. And then we are also going to create, for further processing, another using the statement NumPy array, which basically is a band interleaved stack having the blue, the green, the red, and the infrared channels. Having created the data stacks, we can now plot the data stack using matplotlib. So here you see the data that has been retrieved and being processed as a natural color composite and a false color composite. So it's an area over the Netherlands, and we have retrieved the data using a statement called median time, which gives us a very high likelihood to get a non-clouded or cloud-covered image back. And that is basically what you see over here. So it's an area which is just north of the capital of the Netherlands, Amsterdam. To get the data from a NumPy array back into an ILWIS format, so in this case, we are creating an empty raster using the row, column, and the number of spectral channels, using the georeference as it is read from the variable raster, for a data range from 0 to 255 with a precision of 1. So it's an empty raster, which now by ILWIS with a function array to raster is filled with the NumPy array that has been created over here. So you see that ILWISPy and NumPy fluently work together, and now we can store this enhanced and visualized data set using the 4 spectral channels, not in NumPy, but now we are storing it as an ILWIS map stack. We could also store it as a geotiff using GDAL translate in order to transform it by just uncommenting this option and creating the geotiff, which is now been provided over here. So if you want to work with QGIS, you could, let's say, directly visualize it over here. We have the capability, as I indicated, as one of the operations in ILWIS is the map calculator. So we are basically reloading here the red and the infrared spectral channels from our selected raster import. So the raster bands 2 and the raster bands 3. And then a map calculation like an NDVI is the IR minus the red divided by the IR plus the red. So in this case, monkey tail 1 is defined by the IR variable, and monkey tail 2 is the red variable. And then we are specifying our value range. So the calculation is done using the map calculator in ILWIS, and we can store it as an ILWIS raster map. So you find it over here, the Enkhuizen, with the coordinate system, the georeference, the map, the raster map, the map reference, as well as the binary file with containing the data. Checking the sizes, checking the minimum, the maximum, converting it for visualization into matplotlib. So again, we are reading all the NDVI values, but now the data format is a float 64, as we are having defined it over here using a higher precision with decimals. We create a 1D array using the linear size, and then we are reshaping it back into a 2D array. And then we are using IMShow in order to visualize the data. So here you see the resulting NDVI computed. But let's have a look. And assume that, well, we can do it like this, the NDVI. Assume that this is what our end product and our end user would like to have. We can download the file. We can navigate to the download folder. Put it into our folder. Open the desktop version of ILWIS, and here we have the NDVI. Now in a better color representation. Being able to interact with it, it is often useful to provide it and use it at your local system because you have better possibilities to interact and check the results obtained. So data retrieved from the cloud using the cloud backend is at your fingertips, and if you are satisfied with the final result, then you can simply download it and use your own local processing routines which you prefer. I would like to show you a few other examples. And for that purpose, I have created a few videos which I'm going to activate now. Within this notebook, we are going to retrieve, in this case, a Sentinel-1 image from Google Earth Engine, and we are going to transfer this selected image onto our local cloud service. In order to do so, we are first activating the packages required. In this case, we are also going to make use of ILWIS. And we are going to use the Earth Engine module. We are initializing it, so we have access to the engine. We have used the initialization process in a previous notebook, so everything is already activated. We are selecting an area around the town of Beira, Mozambique, which was affected by a cyclone, the cyclone Idai, during this time period. In this case, we are selecting the vertical send and the horizontal receive polarization. and we are going to create a download definition. And the subsequent downloader, also a definition, which we can use multiple times also to download the other required images. Check if our folder is existing. If it's not existing, it will be created, but in this case it's already existing. And here we are going to enter and activate the definitions and use the settings we have defined previously. If we would click on this link, the image would be downloaded to our local system, but not to the cloud service. But in this case, we have downloaded it in our working directory with a file name download.zip. It's over here. And in order to finalize it, we have to unzip it, and here we have the subsequent files in an ILWISP format. We have downloaded the VH. Now we are going to download also the VV. So we are modifying this, and we want to have the VV for the same area of interest and the same settings. And we have to wait a moment until the file is now available within our folder. So it has been completed, and we now have at our disposal the VV and the VH. So that has been done. Now we are going to use ILWISPy. We set our working directory. We load the two downloaded raster images. We are going now to calculate a cross-polarized image, which is the VV divided by the VH, which is an ILWIS map calculation statement where raster coverage 1 is defined as the VV and raster coverage 2 is defined as the VH, and the calculation performed is monkey tail 1 divided by monkey tail 2, so the VV divided by the VH. Then we set the value range and we store the image as the VC. You could download all the images and create a color composite using the desktop ILWIS 386 software. Here we are going to continue, perform an image stretching, and then we transfer the ILWIS files to a NumPy array. And this NumPy array can then subsequently be used in order to create a plot using matplotlib. So the data is stretched and the value range is now set from 0 to 255. So the stretching has been completed. Now we create a NumPy data stack where we are using the 3 input bands, and this allows us to create a color composite, which is now displayed using matplotlib, and the image is saved as a PNG, and you find it over here. So here you see the impact of the flood caused by the cyclone event, depicted by Sentinel-1.
within this notebook.
But now I would like to highlight another video showing the data which is contained within the Copernicus Climate Data Store. The data from the global flood forecasting system provided by Copernicus and depicting actually the same event.
By the Global Flood Awareness System, GLOFOS. We are loading the required libraries, and the data from GLOFOS is stored at the Copernicus Climate Data Store. In order to access the data, we have to register ourselves, and if we do so, we also are provided with a user ID, which is required. We have to prepare a small file, and you can use Notebook for that purpose. The file should consist of 2 lines. One is the URL linking to the Climate Data Store, and the other line should be your user ID. I have created a dummy file which is shown over here. So the first line is the URL, and the second line is the key which you will be provided with when you have registered. This file should be stored at the root of your system. So in this case, under Home EO Africa. And in order to do so, there is a code field here which lists the present working directory, then moves the text file to a new name, and then subsequently copies this file to the appropriate location. In order for us to check, we are checking and making a listing with the option -A to also see the hidden files in our root folder, and then we rename the file back to our text file. So let's execute this one. And you see the Home EO Africa folder where our API with our user ID is now being stored. We continue installing the CDS API. I have already done this before, so this requirement is satisfied. And as indicated, we are going to have a look at and retrieve the data from the Global Flood Forecasting System, which is part of the Emergency Management Service of Copernicus. So have a look at this website before you really continue. You can also access the data directly via the portal. In this case, we are going to use the API. So we are specifying our output folder. We want to download the data, for example, for 2022, for the Copernicus Emergency Service, the GLOFOS historical data for version 4. The output format is GRIB, gridded binary. The hydrological model used is the LIS flood model, and the product type is consolidated. So it means it has been reanalyzed for the year which is specified over here, for all the days for all the months for our area of interest, and then subsequently we would like to have the file in our data directory with the file name historical underscore the year, in this case 2022, with the extension .grip. When we execute this field, the data request has been sent. At this moment the request is queued, but I have already done this before, and I have retrieved the data for 2022 as well as 2021. So the data for 2021 is simply changing this parameter and executing the field again. Once the data is downloaded, we specify our working catalog, so ILWIS knows where to find the data, and we are going to load the data for 2021 as well as for 2022. Let me just kernel restart, else we have to wait. So once more, we are going to load the libraries. We do not need all of this. We can set our folder directly. We load the data for 2021. We can ignore these grep messages. We said load the data for 2022. Again, we ignore the grep warnings, and now we print the size of the data layers. So you see that so many rows and columns have been retrieved for our area of interest for so many days. So we have daily discharge at our disposal. We check some other metadata. So what is the projection information, which is the window, the minimum and the maximum discharges. And now we are going to transform the data from ILWIS into a NumPy array. Then we are going to append these two arrays, and subsequently we again create a 3D array of the two combined layers. We print the shape. Now you see that 730 layers are at our disposal, representing the daily discharge over these 2 years. Selecting the first layer, we can now create a small plot, and here you see the resulting image of the 1st of January of 2021. And this pixel represents the outlet of the Buzi River. That pixel location is given by this line and column number, and we are going to check the size, and we are going to create a listing of all the pixel values for that pixel. So we have 365 layers, and for that location we have the discharge for each and every day. We are going to do the same for 2021. Here we have done it for, now we are going to do it for 2022. Here we have done it for 2021. And here you see the corresponding discharge for that year. Now we are going to concatenate the two lists. So make a single list out of these two. That list is now consisting of 730 discharge measurements. And we are going to plot or create a plot starting from the 1st of January. And we are generating the timestamp in this case in order to provide us the symbolization for the x-axis. So the x-axis now has a dimension starting at the 1st of January 2021 up till the 31st of December 2022. And now we can plot the data using the date generated and the discharge. So in the plot you now see the discharge derived from the GLOFAS model, the list flood model, for the outlet of the Buzi River over 2 years. Now in a previous notebook you have seen that there was a tremendous flood in 2019. So it would be very nice if you would be able to retrieve also the data for 2019 and 2020, and note that 2020 is a leap year, and create a plot of 4 years instead of the 2 years as it is represented here. Good luck. In this notebook, we are going to look at the data provided by the global flood.
Good. Now I would like to show you another example, which is making use of the data from WAPOR. So the WAPOR database.
We are going to focus on the use of the data provided by the FAO in the so-called WAPOR catalog. Ensure that you have registered yourself using the WAPOR portal. You can sign in and create an account if you want, and you should, in order to continue this exercise, as you need a token in order to access the data. We are using some special tools provided in the folder modules. So some GIS functions, and next to that in the data folder we also have at our disposal a shapefile which we are going to use later. So check the folder and the content. So this library is required. If you have registered on the WAPOR database, then you should have been provided with an API token, and I'm going to include my API token over here and press enter. Now we are going to have a look at the catalog. So you see over here the code, the caption, what is it, the description for the first couple and the last couple of records. We can create a listing also using pandas, so we can display the full catalog, in this case the catalog provided by version 2. And we get a very, very long listing of all the data layers in this catalog. Please review it as a multitude of data over a very long time period at decadal time step or daily time step or aggregated to yearly or monthly time step is at your disposal. Covering the African continent at levels of 250 for the whole continent, for selected basins and countries at 100 meters, and for selected areas even at 30 meters, like here, the level 3. Just to have a look, we are going to have a look here at the level 1 precipitation data. So you see the information here on the precipitation, which is actually derived or provided through CHIRPS, so the Climate Hazard Group infrared precipitation with station data, which is a data set which is often used. Additional information, conversion factors and the like are being provided, as well as the coordinate system of the data. So review this in detail. We can get the cube info and now only the description, the multiplier and the units. Now we are going to check the available data layers for this given time period. So here you see the data up to the end of November 2023, starting from 29. We once more enter our token. Check our data repository in our local system, so here on the cloud service. So in this case the folder was not existing, so the folder has been created. Let's have a look at our current folder. Now we are going to download or use the shapefile and get the limits of our area, plot our shapefile to check it. So here you see the extent of the watershed of the Buzi River, and we are able to, let's say now, for a certain time step, get the data. In this case, the precipitation layer of 2022, decade 36. So if we would activate this link, then the data would be transferred to our local system in our download area. This is not what we want, but that is what you could do. We will continue over here to get the time series from 2009 up to the end of 2022, and we aggregate it over the area of our shapefile. So you see that per decade we have the average precipitation in our catchment area with a minimum and a maximum, as well as the data range for each respective decade is now at our disposal. We can save this to a Comet Delimited worksheet. So if we go here to WAPO data, we have our notebook over here. We can also, and now I just take the center of the window of our shapefile, and for that location, which is now defined over here, we can also get the point precipitation. So not the area average, but the point precipitation, which is provided over here for the time range. Now, as you would have noted, if you inspect the metadata a bit better, we need to multiply the precipitation as it is expressed as the average daily precipitation per decade, so we have to multiply it by the number of days per decade. So for sake of simplicity, the number of days is 10 in a decadal period. So we now have multiplied it by 10. So this is the total precipitation over that decade, which is now saved here as well. We can create a simple graph of the data, and here you find the decadal precipitation over the time series. We can aggregate it to a yearly sum, so instead of using the decade, we are aggregating it to a year. And here we get the pandas data frame, which is giving us the yearly precipitation. The average precipitation is also provided here. With some other climatological data. So you could review whether the precipitation derived, the average precipitation of your time series derived, is matching the one which is derived from the CHIRPS precipitation. I would encourage you to repeat this exercise, but then do it for an area using a point of your preference or a shapefile of your preference. In this notebook, we are going to focus on the
Good, ladies and gentlemen. I have not seen any questions, and I have not seen any chats. But if you still have questions, or if you still want to come up with some remarks, don't hesitate to use this opportunity. We have been now demonstrating a number of portals that can be accessed using openEO. So you have seen examples from the Copernicus data space, Vito, as well as Google Earth Engine, using this capability of openEO, using other API resources. We have been accessing the data from the FAO BAPOR, and in that way, other repositories could also be accessed. But given the limitation of time, I'm not able to show them using this webinar. But if you, let's say, want to access repositories, then, and you have some issues in accessing them, then please don't hesitate to contact me. So as for now, I would like to thank you for attending this webinar, and if there are no further remarks or questions, I'm going to close this session. Thank you very much, and bye-bye.